This is essentially this.
Oh, it is?
Yes, this is glycerol.
Oh, that's glycerol.
50 microliters of water plus food coloring.
Oh, okay. So you've already, that's already pure,
Yeah,
essentially glycerol. We were talking, you know, in the videos I showed you online, when they put the dye in, they pull out this long string of color, which looks crummy. And so he and I both thought of the same solution to that problem.
So you pre-fill the syringe with what we will put in there,
with the glycerol.
and then you pull a little bit of the dye. Then you displace the dye back, and then chase it out with
a little bit of
that,
glycerol.
so you can't pull
and
the
then,
dye.
And then when you pull it out, it'll just be glycerol.
So we'll see what happens.
Hi, my name's Dave Pine. I'm a professor here at NYU.
I'm Andy Hollingsworth, a research professor here at NYU Physics.
So we're going to demonstrate something called hydrodynamic reversibility. We have something called a Couette cell, and it consists of an outer cylinder and an inner cylinder. There's about a 1/2 inch, 1 centimeter gap between the inner cylinder and the outer cylinder, and that's filled with a viscous liquid. Here we're using glycerol. So we'll do the demonstration and then we'll talk about it a little bit. So first thing, Andy's going to put in a droplet of glycerol that's been dyed green, it looks like.
Yes. There we go.
Okay, so now we have a drop of green dye there. And what I'm going to do is I'm going to turn the inner cylinder, and that's going to stretch this droplet of green dye into a thin ribbon. So there we've done around 1 time, 2 times, 3 times, 4 times, and 5 times. So you see the green droplet has now stretched out into a thin green ribbon. Now we'll go back. And there we have our original droplet back to where it started, and showing that the flow of viscous liquids is completely reversible. One thing that makes this possible is the fact that the liquid we're using is glycerol, which is about 1,000 times more viscous than water. It means if you pour it out, it would flow 1,000 times slower. If you do this with water, it turns out that the inertia of the water will be sufficient that when you do this, it won't quite come back, because the water keeps on flowing once you stop inner cylinder turning. But here with a viscous liquid, as soon as you stop the inner cylinder from turning, the liquid stops flowing. And so this is what's known as hydrodynamic reversibility.
Perfect. That's it. One take.
I wonder how fast I can do it. I was a little bit conservative. Let's suppose I go like this.
So there's a speed at which you can spin this where it won't work, where you will not get it to reform its original configuration.
Would it just stay a dispersed band?
It will, yeah, it'll be dispersed.
Well, but it'll come back, but it won't
just
come
won't
back
be as
be quite as tight.
Okay.
Or dramatic.
Yeah, that's working.
Very nice.
Yeah, so it still works quite well, even at that speed.
Mm-hmm.
Here I'll do.
Be here all day.
Wow, perfect.
Yeah, let's go again. Go even faster.
That was pretty good, right?
And we could probably calculate a speed, a velocity at the wall, and therefore generate Reynolds numbers that would, above unity, should start to show the thing not working.